Getting more things done in less time. Sounds pretty good, doesn't it? Hi guys, I'm Josh Nitzadi and I work at Intel doing software and tool development for engineering group. And one of the things I want to talk to you guys about today is a developmental journey I went through as I was trying to get larger and larger simulations in the hands of engineers as quickly as possible. I mean, we want to understand the solution space as best as possible so that we can make educated decisions. And a lot of what I learned is relevant just in any field as you want to scale up processing, lower your processing time, and get more things done in less time. So my problem stems from the fact that I'm using a full factorial DOE. So when you have a design of experiment, you have whatever simulations you have to use. I mean, you can try and plan your experiments really intelligently, but sometimes when you have a very different set of variables you're using all the time, you have to use full factorial, which is the most basic design of experiment, and I'll explain what that means. So let's say we have Galileo over here. He wants to do an experiment. He wants to understand the solution space of things falling. So he takes two balls, different sizes, different masses, and he throws them from the top of the Leaning Tower of Pisa. That's one experiment, or two experiments, one parameter, two values. Somebody says, hey, Galileo, those balls are the same density. What if density has an effect on how things fall in space? So he comes along, brings two balls of different densities, so now he has four experiments, another parameter. Somebody comes along and says, hey, Galileo, you need different shapes. I mean, error resistance, you need to model it correctly. I mean, so he's like, okay, you know what, you're right. Circular objects, square objects, triangular objects, more parameters. Now, I'm only increasing the number of values for each parameter by a little bit. We can increase by a lot, and I'll get into that in a bit. But already, the number of experiments is increased exponentially. Somebody else comes along and says, Galileo, you're dropping everything off the Leaning Tower of Pisa. You need to try other things. So he's like, okay, table, radio tower. Now we have different heights. We're trying to find out how falling objects can be modeled and how we can understand the solution space better. Now, if you're a good designer and engineer, you can reduce your experiments when new parameters are brought in. Like, for example, if I decide to drop objects in space, now the air resistance is negligible and I don't really need to consider the different shapes and all those extra experiments that come up from the triangle, square, and circular objects. I can just drop whatever. It doesn't matter. I mean, on Earth it's pretty similar as well, unless you're dropping a feather relative to, but in general, you can reduce your amount of experiments with careful thinking, but if you have hard to model variables, it becomes hard. So what does this mean for our solution space? Here are some numbers. I'll explain what those mean in a second, but imagine we have a solution space, two-dimensional like this, and I want to find a maximum. Beautiful curve here. Great software, but you can see that there's a maximum, then there's an area where there's a minimum. So I can know, like, okay, you know what, my maximum's over here, I just aim towards the right and the back, and yeah, I have a good maximal value. But that's because I didn't look at enough resolution. As I start to decrease the step between my jumps, instead of looking at two different size balls, now I'm looking at an intermediary size ball, and what do you know? I now have a more complicated solution space. There are local maxima and minima. And this is very relevant, especially if you're looking at fixed values, but in production you may end up with variation that can push you over into a local maxima minima. So you need to really intelligently understand what level of resolution you need in your simulation. So this is a two-dimensional graph. This is showing two parameters, but we can have many parameters. Sometimes we're simulating 20 parameters at a time. And just showing some of the numbers, if I have 5 parameters with 5 values each, we're looking at 3,125 experiments. 7 parameters, 7 values each, almost 1 million. And it scales up very fast. And in our work, there are a lot of variables that can change the relevant value afterwards. So it's important. And getting that computing power and the ability to process all of this is a real struggle. So let's say we're doing things one at a time. This is simple linear computing. This is Galileo on top of his tower, dropping the ball and then dropping the other ball. It takes some time. You know what? He hires some assistants. He's doing some parallel computing now, doing more than one thing at a time. He can hire multiple assistants and he gets more and more workers alongside him. It means the experiments get done faster. There's some considerations into this though. He needs to decide, hey, you do the experiment with these size balls. You do the experiments with the squares. And so you have to divvy up the work amongst the workers. Send them off to the batch workers and decide how you're going to slice them up. And then after all the experiments are done, well, so it looks kind of like this. And after all the experiments are done, you need to then just realize, okay, you got the data from that, you got the data from that, how does this correlate, and collect everything after the fact. It's a lot easier when you're doing it as one person. But once you send it off to multiple workers, you need to collect everything. But it's not a major problem, and it's something that adds a little bit of extra complexity to your code, nothing too crazy. But you do come to another problem as you add workers. You're on a computer. As it gets busier, it gets slower. So you're adding one worker, and one worker takes the time of one worker, relative speed. But as I add more workers, the relative speed of each additional worker goes down. So that this is actually some numbers I modeled. With 5 workers, I was getting to 92% efficiency per worker. With 10, 85%, 30, 80%, and so on. And if you look at the graph on the bottom right, that's the time taken for the total experiment. And on the right axis, the bottom axis, that's the number of workers. So you can see that it's like diminishing returns until eventually there was actually a drop-off point. I believe it was around 90 workers, after which adding more workers added to the time. I mean, Galileo is trying to tell, hey, you need to do this, you need to do this, and nothing gets done because he's too busy sending off all the workers. So you have to think about how to set up your workers and how many to use, how to split it up, and it's a bit of a challenge in itself. But eventually you reach a maximum amount that you can get out of a single computer. I mean, you can see on the left, a snapshot from Task Manager that shows that I was getting pretty close to 100% utilization, and that was good. It was better than when I was doing linear computing, but got to do better than that. I mean, I'm sure you guys know the boss always wants more, he wants it faster, so got to scale up. So I was doing batch processing using MATLAB Parallel Toolbox, which comes with the standard MATLAB. But there's an additional license for MATLAB Parallel Server that enables you to start sending off jobs to other computers as well, as opposed to just the one that you're working on. So you set up a head node, clusters, and then you send jobs to the cluster and it gets divvied up from there. What does that look like? Like this. This is the MATLAB job scheduler on the left. This is what the view looks like in MATLAB. And you can see that you have 2 available nodes. The nodes are the computers that you have your workers on, 4 workers, and 1 job scheduler. So what happens is I send off a job to the job scheduler, and it sends jobs to worker 1, worker 2, worker 3, worker 4. I mean, in that order, it actually goes node by node. I don't know if you guys see an issue with that, but I'll explain why there is. So on the left, I have the MATLAB job scheduler as it is standard. It's doing what's known as vertical scheduling. Vertical scheduling is, as I said, where it fills up node by node so that it will fill up one node entirely, then move to the next. Using some handling of MATLAB objects. A cluster in MATLAB can be handled like an object, and using sending off jobs to different clusters, you can actually schedule your own jobs. So what I did was create a cluster for each node and then just sent jobs to whichever node I wanted to. And with that way I was able to perform what's known as horizontal scheduling, in which I distributed my workload evenly across the workers, across the nodes rather. So what does this look like? Let's start with the first step. I send my first job to both cluster configurations. It's the same. Okay. Nothing special there. I move along to the second job. Now suddenly my node 1 is busy on the conventional cluster, and it's running a little bit slower, as I mentioned before. But with my cluster method, it's running still reasonable. It's not getting slowed down. It's still reasonably efficient. And this problem just continues getting worse as we go along. As we add more workers, as we add more nodes, the benefits of using multiple clusters in that way, it showed itself. And I actually did some analysis after the fact. Here are some rough numbers that I got from real experiments. And I was finding that you have scheduling time as well. It takes time to send off jobs to each of the workers. So you have a certain amount of time in which you expect all your jobs to be sent. In the conventional cluster, we had three nodes completely full, and then the other nodes pretty much empty. I mean, one node that was a third full. Whereas with my method, I had all of the nodes a third full. Now what this meant was, if you look at the graph on the top right, or the table, you can see how I'm operating at 80% efficiency with my cluster, which is to be expected. I mean, you're not going to get 100% efficiency 100% of the time, but the other cluster method is operating at 0.5 something, like 55% efficiency. So there's some disadvantages to this, and in addition to what is just shown here, the scheduling time I actually found increases as the servers get busier. The time taken to send those jobs to the server goes up, and that means that this same experiment, which I ran on both cluster configurations, end up performing significantly faster. We're looking at 50% of the runtime with the exact same resources available, just by changing the way that we schedule our jobs. Now, I brought this information to MathWorks. I showed them some of my results and talked with some engineers there, and I said, hey guys, I'm creating additional overhead by making multiple clusters. I mean, it's not a lot of resources, but effectively there are issues with it. It means managing all the jobs after the fact is a mess, because I need to go through and search, okay, this cluster had these jobs, this cluster had these jobs. It makes it complicated. So I said, hey guys, can you implement something on your end? And so they did. And in testing, it performed better than my method. Not by the same margins, it's better than we're not looking at 50% better, but slightly better. And for me, that was great, because it simplified all the rest of the process. And it meant that managing jobs after the fact was a lot easier, and it allowed me to free my head for just sending more and more jobs. Now, the method they used was actually called round robin, and there are advantages to it, because instead of horizontal scheduling, where I was just sending one by one to each cluster, they were sending jobs to where the clusters were the least busy. So definitely advantages to that. There are still some reasons why I use my old cluster configuration. If I need to provide some weighting, send more jobs to a specific server or less to another. But overall, I mean, where else can you say, hey guys, I have this problem and I want you guys to improve upon it, here's why. And within a month they had a working solution, provided me with good results. So over my journey, I started off, this is another experiment where I initially did it linearly, took 230,000 seconds. That's almost 3 days. I moved to parallel, I got it down to 2 hours. This was with 90 workers on one server. I moved it to parallel server, and I'm down to 30 minutes, which is more than what I expected, and that's actually what brought my suspicion as to the issue with the scheduling. And then after I implemented my fix, I got it down to 15 minutes. So this is an experiment that fully understands a solution space that now an engineer can act within a coffee break. Send it off, come back, and he's ready to go. So that's something that I talked about with MathWorks. They haven't yet implemented. It was something that it is part of the reason why I still use my old method, because I have the cluster objects to which I can give preferential treatment to different servers. But for the most part, the jobs I'm dealing with here are expected all of the jobs to be equal intensity. And it varies. Like sometimes you have a better prediction of how heavy the jobs will be. Sometimes you don't know that much in advance. And so it's hard to keep track of all of that. And it's why you want as much efficiency as you can get before the fact. I mean, basically that's what I wanted to go through. So thanks, guys.